two atoms to qualify as isotope, they must have the same proton. If they have the same number of proton there, they are within the same family. Now you cannot have titanium as an isotope to iron, or magnesium as an isotope to chlorine. Okay? They cannot be isotopes of one another, and they don't even belong to the same family. So isotopes, we're talking about hydrogen, different types of hydrogen. We have hydrogen 1, hydrogen 2, even hydrogen 3. Okay. And chlorine, we have chlorine 35, we have chlorine 37. Okay. So when you talk about the isotope there, and it refers to the atoms within the same family, they have the same atomic number or the same proton number, but they have different number of neutrons there. Okay. Oops, that number didn't come up there. Okay. So for the carbon family there, we have what we call carbon 12, carbon 13, carbon 14. We need you to be able to determine the number of protons, neutrons, and electrons there. So in this case, all of these three different types of carbon atoms, they have the same number of protons, 6. Okay? And they have the same number, well, they have the same number of electrons as well, since proton number is equals to the electrons. So for carbon 12, you would have 6 neutrons. In carbon 13, 7 neutrons. Carbon 14, 8 neutrons. So that's the difference. Again, when you look at the term isotope, you are looking at the same type of atoms. You can't have a carbon and nitrogen as isotopes of one another. They can't be, they're not even related to one another. And yet they have different number of protons. So that's the key thing that you need to pay attention to. And every time when we get to this topic there, people tend to confuse the same mass number with the same atomic number. Now, if two atoms have different number of protons there, they belong to two different categories, two different families there. They cannot be isotopes of one another. Yeah. So this is something that you want to pay attention to. Now, how do we know? How do we know how many particles, how many protons, how many electrons, and how many neutrons are in a particular type of atom there? And plus, when we have different types of isotopes there, how do we know which one has what kind of percentage in it? Now, we use the term carbon atom. We're talking about the carbon in nature there. Well, we don't specify carbon 12, carbon 13, carbon 14 there. But there are 3 different types of carbon. Which one are you talking about? Well, how are they different from one another? In the laboratory there, we can have a what we call a mass spectrometer. Now, the mass spectrometer works the way that if you collect a particular element occurring naturally, and you subject it into the mass spectrometer. Now, mass spectrometer uses a high energy electron beam to bombard the atoms that you collected. And as a result, you can actually knock off one of the electrons from those atoms. Now, when you have equal number of protons and electrons, there is no net charge in that atom. But if you put that sample in the mass spectrometer there, you knock off one of the electrons, the particle becomes positively charged because one of the negative charge is being removed. Now, if you subject that positively charged particle and going through an electric field and going through a magnetic field, now, based on the mass difference, we may have different number of neutrons in there. Based on the mass difference, now those different particles with different mass will actually go through a path slightly different. So we can actually determine which one, the heavier particle will stay, say, on one side of the spectrum there, and then the lighter particle will bend a little bit more because the path and you have the same charge there. A lighter particle and being accelerated and going through a magnetic field there, their path will be bended a little bit more. So we can actually tell, using the mass spectrometer, we can actually tell for any given elements there, we can figure out how many different types of isotopes or how many different types of isotopes we have here. So for carbon, we would have 3, carbon 12, carbon 13, carbon 14 there. And each atom, each type of elements, they will have different number of protons and neutrons and different types of, different number of isotopes there. Now, when you look at, say, one of the, taking one of the atom from the periodic table there. Now, neon, naturally occurring neon, we have 3 different types of neon. We call them neon 20, neon 21, neon 22. The relative mass, and you saw this term atomic mass unit. So if you identify carbon-12, one of the isotopes of the 3 carbon atoms there, if you define carbon-12 as exactly 12 atomic mass unit, you compare neon-20 to it, well, neon-20 will have an atomic mass unit of somewhere around 20, 19.9924. Okay, so these are the 3 isotopes of neon. Carbon has 3 isotopes, neon has 3 isotopes, but not everybody has 3 isotopes there. And the hydrogen has 3, the chlorine only has 2, fluorine only has 2. Okay, so naturally occurring elements, they have different number of isotopes there. Now, if you look at neon there, in the periodic table, you see neon is element number 10. The atomic mass given is 20.1797. It's neither 19.9924 nor 20.9938 nor 21.9914. It's actually a weighted average of all of these numbers. So whatever number you see as the mass number for the atom there, we have to take into consideration of all the naturally occurring isotopes for that particular element. And we need to determine the percentage of each type of isotope and then multiply the relative atomic mass of each isotope by that percentage. We add them together, come up with a different number. So this is how we determine, when you look at the periodic table there, the atomic mass is the weighted average of all naturally occurring isotopes there. Now we have done, we have done enough research, and we've done for all of the elements that we know of, we have already determined the number of isotopes for each atom, but for each element there, we determined their percentage, relative abundance there, and we determined the relative percentage of each of the isotopes for any element that we know, and we already calculate the weighted average there. So that's the number we have in the periodic table. Okay, so the atomic mass, well, we tend to use the term mass over weight because mass is a constant number. It does not change no matter where you are. If you're on the moon, your mass is 150 kilograms. Kilogram would be a little bit too much. Well, I'll say 150 pounds and talking about mass there. You're on the Earth, your mass is still 150 pounds. But weight is different, and depending on the gravitational force there. And your weight is only 1/6 when you go to the moon. Compared to when you're on the Earth here. So atomic mass, atomic weight. Well, this term, atomic weight, we've been trying to phase that term out for the past 30 years, but people still sometimes say atomic weight. So in this particular course, sometimes I will try to remember and we use the correct term atomic mass, but every once in a while you will hear me say atomic weight. So these 2 terms are used interchangeably. Okay. And the more accurate, the correct term should be atomic mass. But sometimes you hear in the evening paper published in this scientific literature there, and you see the term atomic weight, and they mean the same thing. Okay. So how do we determine the number of isotopes there? And we talk about the mass spectrometer. Okay. So if you take neon, you subject neon, naturally occurring neon, in the mass spectrometer, you will end up with 3 lines in it. Now those 3 lines indicate the relative percentage, well, the percentage in terms of, we call it a relative abundance state. Okay, so